I'm going to show you how to rotate a left outside heavy tree. So if we start with a tree that has a left child that also has a left child, that's going to be left outside heavy. So this root has a balance factor of +2, and then this child has a balance factor of +1. So we're going to um, rotate to the right and we're going to pivot around the unbalanced node because this one has a balance factor of 2. So um, this node is going to become the new right child of 20. So 30 will go here, and then 10 will remain the left child of 20. So this is a right rotation, and now the tree is balanced. Next, we have a right inside heavy tree. It becomes right inside heavy when there is a right child to an imbalanced node, and it has a left child. So the new node inserted is heavy on the inside. To fix this, we'll need 2 rotations. So first, we'll start with the child of the imbalanced node, because this one has a balance factor of -2. And then this one has a balance factor of 1. So we're going to start with node 10, and we're going to do a right rotation on it, which means that 7, its left child, um, or the original node becomes the new right child of its left child. So 7's going to move up, 10 is going to become the right child, and then 5 will still remain at the top. And then finally, to balance the whole thing, we'll do a left rotate pivoting at the 5. So 5 is going to move down, 7 will go to the top, and then 10 will be the right child of 7. So now this is a balanced tree. Now I'm going to show how to calculate the height and balance factors. So the height is calculated by taking the max out of the height of the left child and right child, and then adding 1 because the height of the node we're calculating is 1 higher than the left and right subtrees. And then for the balance factor, we're just going to subtract the height of the left. We're going to subtract the right from the left. So these are the children. Um, so our first example, we'll do this. So the balance fact, so we'll get the height of each one first. So for number 4, the height, we'll first check the left one's height, which is 0, and the right one's height, which is 6. So, or I mean 0 again. So it's the same for both of them. We could pick each or either one, and we're just going to add 1 to that. So the height is 1. And then the balance factor is going to be the height of the left minus the height of the right. So we have 0 for here and then 0 here. So the balance is 0. Now for the node 2, the height is going to be the height of the maximum of the height of its left and right childs. Um, in the height function that we write in our code, that's going to return -1. So the maximum out of that is just going to be -1. Then we add that 1 at the end to calculate this one's height. So its height will just be 0. Um, and then for its balance factor, there is no left child, so that's going to return a -1. But there's also no right child, so that's also going to return a -1. And then -1 minus -1 is 0. So 6 is exactly the same structure. So it's going to have a height of 0 and a balance factor of 0. Now, if we had a tree that looked different, then now the height of this one is going to be the max out of the left and right child. So the right child doesn't exist. The left child has a height of 1. So that's going to return 1. Also, we might as well put that height in here now. Or sorry, this is going to return 2 because we're adding it. So 1. This one has a height of 1. And then this one has a height of 0 because it has no children. Now, the balance factor of this bottom one is going to be the same as the leaves over here, so 0. The balance factor of this one is going to be the height of its left child, 0, minus a -1, because there's a null pointer for the right child. So the balance is 1. And then for the node 4, its balance will be the height of the left child, which is 1, minus the height of a null pointer, which is -1. So 1 minus -1 is going to be a balance of 2. So since 2 is too big, node 4 is not balanced. I'm going to explain the level by level printing using a queue to traverse the tree. So let's make an example tree right here. We could do this. And we will start with the root. So let's have a queue over here. How do I spell that? Another E. Um, and then let's keep track of the output over here. So first, we're going to insert the root into the queue. So 4 will go in the front. Um, then we are going to start the while loop. Um, so while the queue isn't empty, we're going to pop the front. So 4 is gone. We're going to keep track of what we just popped. We're going to output its data, which is 4, and then we're also going to output its height. When we calculate it, it will turn out to be 1. And we're also going to display its balance factor. So there's a height of 0 here, a height of 0 here. When those are subtracted from each other, it's balanced. So that's going to be a balance factor of 0. Um, and then after everything's displayed, we are going to add its children to the queue. So the left child will be pushed into the queue, and then the right child will also go in the queue. And now, since we've already done everything on that level, the for loop is going to break, and we're going to start over again, popping stuff from the queue on a new line. So this is the first line with just 4. The second line, we're gonna pop the 2. So we'll have a 2 here. Its height is 0 and its balance factor is 0 because it's a leaf. Um, and then we're gonna add its children to the queue, but since it doesn't have any children, nothing gets added to the queue. And then we're gonna pop the 6. So 6 will go here, its height and its balance factor. Since 6 doesn't have any children, nothing new is being added to the queue. The for loop that is popping stuff out of the queue is going to end at the end of the level again. And then when we exit that, uh, we'll see that the while loop is not going to execute anymore because now the queue is empty because no children were added to it during its last iteration. So this is the final output. It shows the first level has a 4, the second level has a 2 and a 6, and all of them show their heights and balance factors. Hello, this is my AVL assignment right here, and I'm going to run it real quick to show that it works. So right here I have an input text with just a bunch of random integers, not in any particular order. And then here I have an output text already, but it's empty. If you don't have one when you run this, it'll just create one for you. Um, so here we go. If we look at this, everything should be in the right spot. So I'll just show that really quick. There's a 10 at the top. Oh, oops. Then 6 and 40. then 3 and 7, and 29 and 48, and then a 2, a 12 would go over here, and a 99. So everything was output level by level. It shows the height and balance of everything. And drawing out the entire tree, everything looks balanced. Everything's on its right level and everything's sorted. So it looks good. Now I'm going to explain the code. So in the header, I have the algorithm, which I use the max function. And then fstream is so I can handle input and output files, reading and writing to them. Uh, SStream helps with formatting strings, and then Q is going to come in handy in the function that displays all the levels of the tree. So first, I define the node structure to for all the nodes that are going to be in the AVL tree. So each node has a left child, a right child, its own data, and its own height. And when nodes are initialized, they're going to start with that data value passed in. They're not going to have any children to start, and their height will be 0. So the first helper function is getting the height of a node. So you pass a node in. If the node isn't a null pointer, then you can safely return the node's height. If it is a null pointer, just return -1 by default. Um, Returning -1 is going to help when you get the balance of it, because a null pointer will return -1 when checking for balance. So then here's the get balance function. You pass in a node. If it's not a null pointer, you can use height. Um, Height of the left node minus height of the right node is the formula for balance. And notice that the height function, if the left child or the right child is a null pointer, the height function is going to return -1. So that's what it should return for getting the balance of it. And then otherwise, if the node doesn't point to anything, just return 0. Okay, so for the rotation functions, first we have right rotate for a left-heavy subtree. So let's say we have a tree where we pass in the root of the tree is B, and this is left-heavy. So there's a value A to the left of it, and then A has a left child too, and this is not balanced. So to rotate this, we want to um, initialize A here, and then we also want to initialize AR if that exists, because AR is going to become the left child of B. So the right child of A, if it exists, will be initialized there. And then when the rotation happens, we're going to make B become the right child of A, and we're going to make AR be the left child of B, and then X is still the left child of A. So this new tree is balanced. And these last two lines are going to update the heights by picking the maximum height between the left path and the right path. And then it's going to return the new root of the tree, which is A. The left function works almost exactly the same. It's just mirrored. So you can probably imagine that. Okay, here's the rebalance function that's going to be used inside of the insert function to rebalance every time a child is added to a node. So this will be called on the current node that had a child added below it, which means the first thing we have to do is update the height and then get the balance factor to see what case it is. So there are 4 imbalance cases. The first one is left left, meaning it's outside heavy. So that one's straightforward, and all you have to do is right rotate. The next one is a right right imbalance. So it's outside heavy. That's just one rotation, the left rotate. And then if it's left right, so it's inside heavy, it needs 2 rotations. So you rotate the child to the left, and then you rotate the current node to the right. And then the last case, right left, is inside heavy two, so that's two rotations. The child is rotated to the right, and then the current node's rotated to the left. And if it gets through all these checks without any imbalances, then it'll just return the node how it was because it doesn't need any rotations. Here's the insert node. You pass in the root of an AVL tree and then the data of the new node you want to insert. So it takes in the key. If the root of the tree is a null pointer right away, it's just going to return a new node with the key because it's making a new AVL tree. And if the key happens to be equal to the data of the root of the tree, it's just going to return the node that was passed in because the key's already in there, so it doesn't need to make a duplicate. And now it can start the recursive process. If the key is less than the node's data, it's going to move to the left down the tree because it's less than. So it's going to call insert again on the left child. Otherwise, the key is greater than the node's data, so it's going to move right down the tree and call insert on the right child. And then it'll keep doing this recursively until it moves down to the tree, down the tree, and uh, and then once it either finds the node or reaches the bottom of the tree or something, it's going to call rebalance and work its way back up the tree. So rebalance, every time it rebalances a node, it's going to return the root of the tree that is balanced if it changes. And then finally, when we're done calling rebalance, it's going to just return the root of the new tree that is now balanced and has that key in it. So print level order is going to make use of the queue to traverse the tree level by level. So you pass in the root of the tree that you want to display and then pass in the file you want to write your display to. And in the beginning, you have to make sure that the root isn't a null pointer. Otherwise, you're just going to return right away. You don't print anything. Then you make a queue, and the first thing you're going to do is push the root to it because that's the first level. And this loop is going to repeat until the queue is empty. First, it's going to find the queue size, which is going to be the size of the current level that it's on. And then the for loop can execute that many number of times. And while that loop executes, it's going to have keep track of the current node at the front of the queue, and then it's going to pop the queue one at a time each time it goes through the loop. And it's going to display the data of that node that was popped, and also its height and its balance. And then while it's on that current node, it's going to add the left and right child of the current node to the queue for the next level. And then as it goes through here, it's popping everything that was on the current level, and then also populating the next level at the same time. But it's going to end when the current level finishes because of num. And then when it comes back up here, it's going to update num and then do it again with the next level. And then at the end of each, like every time a level finishes, a new line will be printed. So we can see each level, all the numbers will come out on one level. And then finally in main, the root of the tree is declared. Um, and it's going to be initialized with a null pointer because we're going to populate it with the input file. So then the input file is opened, the output file is opened. Just check if the opening was successful, like maybe there's no input text in the directory. Um, and then just declare a variable so we can read all the ints from the file. So it'll just take each one separated by a space or a new line and insert it into the tree. And we start with like the root we had in the beginning, but this insert's gonna insert a new root if necessary every time it inserts, or it's gonna return a new root every time, or the same old root every time a value's input, depending on if it needed to be rebalanced. And then after the tree is populated, uh, we just print it with our print level function, and then we close the files, and everything shows up in your output text.